One kind of hypothesis is the null hypothesis. And this stuff's got strange names. It's not that difficult. So you got a null hypothesis, you got an alternative hypothesis. There's two types of error, and there should be some stuff in between here. You got two types of error, but with those hypotheses, you can only make certain decisions, and we'll talk about those. Determine whether you got a one-tailed or a two-tailed. We talked about that earlier in the year with the one-tail or the two-tail, and make sure I talk about it when we get to it in here, because this is one of the things I don't think is in this PowerPoint. We have our normal curve. If we expect our mu to be here or higher, then this is the part. This time, instead of seeing where the mu actually falls at, we're trying to see, when we do these hypotheses and testing, we're trying to see, does it fall outside of that range? So we can say, hey, this is messed up. You know, the tires Jesse bought aren't good tires because they didn't last the 40,000 miles or 50,000 miles or whatever they're supposed to. So we're trying to actually see if it's in here, and what we're going to call this is just sort of common sense. This is a left-tailed. That would be a right-tailed. Then you can probably guess a two-tailed is something like that, where you want the mu to only fall in there. And it doesn't have to be mu. It could be P. It could be whatever. Determine whether make and interpret decision based on the results of a statistical test. That's what we're going to do. We're going to make decisions. Hey, you know, is this a good setup? Is it a poor setup? Is it whatever? Be able to write a conclusion for your hypothesis test. You'll be able to decide this medicine is not effective to cure whatever, something, cancer or whatever it happens to be. All right, a hypothesis test. Write this part down. Pretty important. A hypothesis test is a process that uses sample statistics to test a claim about a population parameter. Remember, we talked about this way back at the start of the year. When you're doing a sample, it's called a statistic. When you're doing the population, it's called a parameter. So if we were dealing with something like, if we were dealing with the mean, then our statistic would be X bar, and our parameter would be mu. Sample statistic, population parameter. Don't bother with writing down the example here, but this is just to help you out. For example, an automobile manufacturer advertises that its new hybrid car has a mean mileage of 50 miles per gallon. To test this claim, first of all, to test it, are we going to be able to take every one of their cars and take them out and drive them for thousands of miles and do the whole population? No, it doesn't make sense. So we're going to have to take a sample, drive those samples, see if they get 50 miles to the gallon on the average, and decide whether their advertisement is wrong or not. Now, what if we take a sample and figure out that they get like 48 miles per gallon? Does that mean that they were ripping us off? Not necessarily. That's pretty close, right? And that's what we're going to decide. You know, that range, like we were doing last chapter, that range, you know, it should fall within this certain area here. If it falls outside of it, then that's when we can say, hey, something's not right here. Do what, Grant?
Do you like allowed to round them by like 1%
See, and that's what that is a standard deviation. And the government allows
One standard deviation.
them to be so far off
They
of
give
their.
them one standard deviation up or
It's-
down, and they always
it's-
go up.
Right, it's
Why would
probably,
you go down?
it might be, 2 standard deviations. It depends
It's
on
like 1
how exact you wanna be. And that's part of what we're gonna talk about. So that's what we're gonna be doing this chapter. Hypothesis test, just taking that sample statistic and testing the claim about the population. Different uses for this. Marketing strategies, new medicines and treatments. When you get new medicines and treatments, that's probably where Carson will be here in a year or two doing all those things he hears on the radio where they pay you $50 to come in for a weekend and test out these new medicines, and you'll be making a living doing that, right? I don't think your dad would be too happy if you were. I'd be, you wouldn't be living at the house anymore. But that's what they're doing there, is they're testing those medicines. They're taking a sample and testing them. Now, some of those things, and we'll probably talk about this as the chapter goes along, when they test a new medicine, if I take Jacob M over here in, and I say, okay, this medicine's gonna cure insomnia. So when you can't sleep at night, this is actually gonna help make you sleep. Might he sleep better just because I told him that? Yeah, so what they do is,
They don't tell you what
they have sometimes they'll have a placebo, what's called a placebo, and they give some people the placebo, some people the real thing, so that you can tell the difference, whether it's the actual medicine doing it or just the idea that, hey, you're thinking that this is supposed to help you do this. All right, this is important. Might want to write this down. Central limit theorem. We talked about that a couple of chapters ago. If n is greater than or equal to 30, then the sample means will always be normally distributed. If they tell you the means, the sample means is normally distributed, then, or if the population is normally distributed, then we can just use any n. So it wouldn't have to be 30. It could be 10, it could be 12. And then these are the 2 formulas for variance and standard deviation that we covered a couple chapters ago. With this says, when you get down to here, this is variance, that's sigma squared, and this is sub x bar, so it's like this. It's got the sigma squared, but it's a sigma squared for x bar. Sort of hard for me to put it on there without making it too big. That's not 2 over x, that's sigma squared for the x bar, subscript x bar there. And then the same thing on the standard deviation down there at the bottom. This is stuff, we probably won't use any of this really today on the assignments and stuff today, but as we go throughout the chapter, we will. remember with some of this stuff, make sure you write down this stuff carefully. I've seen on some of the tests where some of you, when we had that square root of n on the bottom, some people forgot to take the square root. Like it didn't get written down in your formula or something. So make sure that you're writing down the formulas correctly.
Why is it so hot here?
Normal curve again. Again, we already went over this. I'm not going to go back over it again. Remember, if you're dealing with z-scores, standard deviations this way, standard deviations that way. If we're dealing with raw scores, then these numbers might be something different, and we'll talk about that as the chapter goes along. Statistical hypothesis, a statement or claim about a population parameter. So this is what we're going to be doing. We're going to make a statistical hypothesis. So we're going to make a claim, or actually usually we will not make the claim. We'll let the company make the claim, and then we'll test it. You need a pair of hypotheses, one that represents the claim and one that represents its complement. When I say its complement, that means everything else. It's like when we were doing probabilities a few chapters ago, and the probability of rolling a 5 on a die is 1 out of 6. Well, the probability of not rolling a 5 on a die then is everything else, which would be 5 out of 6. That's sort of the same thing here. It's got to be where you have two possible outcomes. It's either true or it's false. It's either correct or it's incorrect.
Spell hypothesis. No, because the correct spelling is right above it.
Now you just know because there's two different spellings up there. So which one's correct, Grant?
The top one? Isn't that the plural?
Hypotheses. Oh, yeah, it is.
Oh, snap. He got served so hard.
Tell me I'm wrong. I probably didn't even make up a slice of that. Because if I would, I probably would have spelled it wrong the second time. When one of these hypotheses is false, the other must be true. So when we make up these two things, one of them's true, the other one's got to be false. They can't overlap each other, because then you could have things that you're saying are true and false at the same time. So they got to be two completely separate things. One of them, when one of them's false, the other one has to be true. So if I gave you a set of numbers, maybe this circle here's got 1, 3, 5, 7, so on and so on in it. And I gave you another set of numbers, 2, 4, 6, 8. And you're looking for the answer. Either the answer comes from this set or it comes from this set. It can't come from both at the same time. So one's got to be true while the other one's false. All right, the null hypothesis. This is probably the most important thing in this whole chapter. Null hypothesis. The null hypothesis always has to have an equality statement in it. And that's one of these three. Less than or equal to, greater than or equal to. So when you're doing the null hypothesis, it's always got to have one of those in it. So mu is less than or equal to 75. That could be a null hypothesis. Always got to have that equal to part in it. If that's the case, then here in a second, I'm going to put up the alternative, sorry, be out of the way, alternative hypothesis, what's it gonna have in it? If the null hypothesis has those three, what's the alternative gonna have in it?
Less than or greater than?
Less than, greater than, one other one. Not equal to. So the alternative hypothesis is always gonna have one of those three. The null hypothesis has to have one of these three in it. We were talking about the tails a little while ago. When you're looking at these, this one, we're saying something like mu is less than whatever. So we want mu to be that way. So the part that we don't want would be on the right. This would be a right tail, left tail, and then the not equal to is the one where it goes out both directions from two certain points. So that'd be two-tailed. We'll talk more about that. The null hypothesis, that's the symbol for the null hypothesis, H sub O. H sub O, null hypothesis. You're going to use that on just about every problem we do this whole chapter. You're going to start off, you're going to say, okay, I got to write a null hypothesis. So you're going to start off HO. And then we'll say whatever the null hypothesis is. It might be something like P is greater than or equal to 0.28. Means the probability of this occurring is greater than or equal to 0.28. That would be our null hypothesis. Our other one, instead of HO, it's HA. A stands for alternative. And they got to be complements of each other, and we'll talk about this more. But so this one would be P. If you write the null hypothesis as P is greater than or equal to 0.28, then the alternative hypothesis has got to be everything else. So instead of wanting greater than or equal to, we want everything less than 0.28. And that would take care of everything. That involves all of the probabilities. So you got a null hypothesis, you got an alternative hypothesis. Either this one's true or this one's true. And you probably never ever hear me say H not. I think it's got another. Oops, better erase this so you can see this. Alternative hypothesis, what I said a second ago. I'm just going to put the other part up here since I already said it. Must be true when HO is false, and it's always denoted HA, H sub A. So what you're doing with these is you're making up a statement. You have a statement, the M&M's Mars company says that every bag of M&M's contains
Hello,
2.8 grams.
Sorry for the interruption. Today is the blood drive, so student council members will be retrieving students from their classroom about 5 minutes before they are signed up to give blood. Students who are giving blood must wait until the student council member shows up with their green blood drive pass. Students are not allowed to leave the room without a pass. Also, students, be sure to bring a photo ID with you when you give blood. If you do not have a photo ID, we will provide you with a form of ID from our online system. Thank you and have a nice day. And could I also please have Katie Beener, Callista Kisling, Tyler Glander, and Weston Hawes please report to the high school office. Thank you.
So if they're saying that there's 2.8 grams of M&M's in every bag, the mu then is 2.8 grams. Our null hypothesis, what we could say then, is that mu equals 2.8. What would the alternative hypothesis be? If they're saying that every bag has 2.8 in it, what would the alternative be? What's everything else other than this?
Everything else.
So how would I write it? Mu
It's not equal.
does not equal 2.8. Now, they probably don't say that mu is equals exactly 2.8 because they know that's not going to come out to be true every time. They're probably saying mu is at least 2.8. So it might be one of these other two symbols in there that we use, and then we'd have to switch it around for the alternative hypothesis. And when we look at these, we're going to do testing on them and decide, hey, one of those two has to be correct. Okay, are they correct? Or is this alternative hypothesis correct? And one of them has to be correct. These are called complement statements because it involves everything that could possibly be involved in that certain situation. There's nothing left out that you could have some strange thing happen and a bag M&Ms isn't one of these two. That's not possible. All right, to test the population parameter. First thing you do, you state the null hypothesis and the alternative hypothesis. Then we're going to go through and we're going to prove that one of them is true or false. We'll prove what we'll actually base this on, and that this is, I didn't write this right. This actually should be, we go through and we actually prove the null. We decide according to the null. Is the null true or is it false? So is that null hypothesis correct or is it incorrect? If one of them is true, then that means the other one has to be false. If one of them is false, then that means the other one has to be true. So an example here, our null hypothesis, HO equals 5. Then we write the HA would not equal 5. Another example, HO is greater than or equal to 70, then HA has to be less than 70. Now where you got to be careful on these, if I just make up something here, let's say we got a statement and a problem, and it says mu is greater than, I don't know, give me a number. 10. Mu is greater than 10. And what we have to do is we have to write the null and the alternative hypothesis. So first we write the null. Is this going to be the null? Because it's got to have the equal to sign in it, right? So what's the complement of mu is greater than 10?
9.
Mu is, still uses the same number. Instead of greater than, it's going to be less than or equal to 10. So that's our null hypothesis. Our alternative hypothesis, if I can get my pen to work, is going to be that right there. Mu is greater than 10. And what you have to do anytime you're writing these, write down which one is the original claim. The original claim this time, what the company or what Sean said, mu was greater than 10, that was the original claim. The original claim is not always going to be your null hypothesis. It could be the alternative. Okay, so the null hypothesis always has to have that equal to part in it. Alternative is everything else. And in prob stats, the average age of a student is 16. So this is my statement. I'm saying in prob and stats, the average age of a student is 17 years old. All right? So that's my mu, and I'm saying it equals 17. When we go to write the null hypothesis, the HO, and we go to write the HA, the alternative hypothesis, we're going to have, this one, remember, has got to have the equal to in it, or the less than or equal to, or greater than or equal to. So this is going to actually be our null hypothesis this time. So mu equals 17. What would my alternative hypothesis be? Mu does not equal 17. And again, I forget to do this all the time, so you'll have to help me. This was our original claim, and we got to label that as our original claim, so we know which one was stated originally. Ron, that make any sense?
Actually, kind of makes sense.
And what we're going to do with these is we're somehow going to test them. Now, we're not going to worry about testing them so much today because I want to make sure that you understand how to write them and everything just today, but we're going to test them. The other thing that we should do on this, some things you got to remember. If I'm saying mu equals 17, if I go to graph that, I got 17 right here. The graph of mu equals 17 is just a dot on 17 on a number line, right? That's just a dot. How would I graph this one? Mu does not equal 17. Anybody remember that from your algebra days? We put 17 right here. Do I want to put a dot on 17? You want to put a open dot on 17. And where do I shade at? Both ways, right? Shade this, shade the arrow, shade this, shade the arrow. What if I had this? Mu is less than 12. How would I graph that?
You shade from 11 down. Is it 12?
Start at 12, and what kind of dot goes on 12?
Wouldn't it be like some type of error or something?
A circle?
Open dot, and which way do I want to shade?
Yeah, that makes sense, because it doesn't count.
Shade this way. What if I stuck that on there?
Then you shade it in. That's
Then you
what I'm
shade
saying.
in the dot on 12, and it includes that. All right? So you got to remember that. If it's got the equal to, then it's a solid dot, and you're shading whichever way you're going. So let's try another one. Mu is greater than or equal to 6.
Solid dot.
It's all the,
Solid dot on 6.
And you're going.
do the right.
Shade that way, shade in the arrow, so it keeps going forever and ever. Now what, if this is our null hypothesis, what would the alternative hypothesis be for that? If mu is greater than or equal to 6, now we're going to say mu is what? Less than 6, just less than 6. And if we had to graph that, got 6, what kind of dot's going to go on the 6? Open, and we shade everything this way. So looking at these two graphs, do they include the whole number line? Yeah. All right, so whatever this one doesn't have, this one has. So there's no empty spaces there. So everything's got to fall in there somewhere. To write null and alternative hypothesis, translate the claim made about the population parameter. So you're going to translate it from words into a mathematical statement, like we just did there. Then write its complement. That's what we were just doing. These are 3 different things that could happen. These are all the ways that your null and alternative hypothesis could look. K is just some random number or variable. So your null could say mu is less than or equal to K. If it says that, then your alternative hypothesis is going to be mu is greater than K. mu is greater than or equal to k, then your alternative hypothesis is going to be mu is less than k. Mu equals k, then your alternative hypothesis is going to be mu does not equal k. So those are all the possible ways that you could set up the null and the alternative hypothesis. Regardless of which pair of hypotheses you use, always assume that mu equals k. So what they're saying there is when you're looking at it, assume that mu is in that range. So if it's like this, the mu's in here. Got a blank slide. Write a claim as a mathematics sentence, state the null and alternative hypothesis, identify which represents the claim. This is what you're going to do on the homework. So watch closely on this. University publicizes that the proportion, remember when we're talking about proportion, that's the percents, like the p-hat from last chapter, of its students that graduate in 4 years is 82%. So they're saying 82%, so P equals, let me make sure here, yep, 0.82. That's their claim, that P equals 0.82. Does that make sense? Shania, that makes sense? So all I did was translated it from words into a math looking thing. Now what we want to do is we want to write a null and an alternative hypothesis for that. Our null hypothesis, our alternative, and we're going to tell which is the claim when we get through with that. So our first thing, we look here, this is the statement that we wrote out. It's got the equal to sign in it. So is that going to be our null or our alternative?
No.
That's the null, because it's got equal to in it. So we're just going to say P equals 0.82. That's our null. What's our alternative hypothesis going to be then? Is not equal to 0.82. Which one of those was the claim? And again, I forgot it again.
No.
This one was the claim, so out here beside it, write claim. That's what we want to know. That's to write them. That's all. That's basically all we're going to be doing for today, or a lot of what we're going to be doing today. So the solution, we got our null, alternative, equal to, we just did all that. That's the complement, not equal to. We wanted to graph them. Remember, if you were graphing them, if we graph the null, put 0.82 in here. We want it to be equal to, so it'd just be a dot on 0.82. Then the alternative hypothesis, put 0.82 in here. Open dot, and it's everything else. It's all this, and it's all that. They've got to be complements of each other. It's got to be where everything that's possible in this situation is either in this graph or in that graph. A water faucet manufacturer announces that the mean flow rate of a certain type of faucet is less than 2.5 gallons per minute. I don't know why they would announce that, because when you have a faucet, do you want it to be less than something? If you have a faucet, you want to show it's got power, right? And it puts out a bunch. So I'm not sure why they would announce that. So we change this. How am I going to write that? This time, instead of dealing with P, we're dealing with what? Mu. So it's mu. Is it an equal to sign? Less than 2.5. That's the original statement. we go to write our null hypothesis and our alternative hypothesis. Well, this original claim is going to be which one of these two? That's going to be the alternative this time. Mu is less than 2.5. That's the original claim. What's this going to be then? Our null hypothesis. This is less than, this has to be what?
Greater than 2.5.
Greater than or equal to 2.5. Remember, the null hypothesis always has to have that equal to part in that statement. A cereal company advertises that the mean weight of the contents of its 20-ounce size cereal boxes is more than 20 ounces. So their claim this time, it's more than 20 ounces. So that's mu, because we're dealing with mean again. What symbol am I going to use this time if it's more than 20 ounces? Greater than, right? Just greater than 20. What's my null and alternative hypothesis going to be? Is this going to be the null or the alternative? That's going to be the alternative again. And that's your claim. And then what's our null hypothesis? Less than or equal to 20. So we check this and see, when we go to do these tests, we're going to see, is this cereal company lying to us and, you know, leaving out an ounce here, ounce there, so that they can sell more product or save money. So that's the original claim. We said that. That would be our null hypothesis. It's the complement of the original claim. All right, there's two types of errors. There's two different types of errors, and this probably shouldn't be here. That's on the next slide. No matter which hypothesis represents a claim, always begin with the hypothesis testing, assuming that the equality condition or the null hypothesis is true. So we're always going to start off thinking the null hypothesis is true. No matter what, no matter which one's the claim, we're going to assume that the null hypothesis is true. I sort of said this a little while ago. You're always going to take that HO, and that's the part where you're either going to prove or disprove that null hypothesis. But we're always going to start off assuming it's true. At the end of the test, one of two decisions will be made. These are the only two decisions you can make. And this is important. These are the two decisions you can make when we're doing this testing. You can either reject the null hypothesis or fail to reject the null hypothesis. So either you reject what the HO says or you fail to reject it. Now this is where it gets a little hard because I'm not a Mr. Eiler or anybody who can do this wordplay stuff, like on a debate team or something, like a Donald Trump or one of these politicians. I'm not good at this stuff. All right? When I say I reject the null hypothesis, does that mean the null hypothesis is wrong? No, I'm just saying that, I don't really believe it. When I say I fail to reject it, does that mean I'm saying it's correct? No, it's just saying, you know what, I'm not really sure if it's correct or not, but I'm not going to reject it at this time. So it's like being a politician. You're not really making a clear statement. They're doing the healthcare stuff right now, and they're saying, oh yeah, this healthcare bill is going to be great. And then the next words out of their mouth are, oh well, it's not a very good bill because it doesn't cover everybody like it should. So we either reject the null or we fail to reject. And when you do that, that's when the errors come in. Because your decision is based on the sample, the possibility of making, there is a possibility of making the wrong decision. So if I'm doing a sample, if I sample all you guys and let's say we figure out that your favorite fruit is oranges. Can I just say that that's the favorite fruit of the school? No, there's a chance that that might not work out because we're dealing with a sample. All right, these errors, these are important. The box, I don't know that I'm really concerned about the box, but type 1 and type 2 errors, you got to know what they are. So write them down. Let me move that out of the way. The box is just telling us there's 4 different things that could happen. If the null hypothesis is true, and we say it's true, then we made a correct decision. If the null hypothesis isn't true, and we say it's true, then we made an error. Type 1 error. Type 1 error occurs if null hypothesis is rejected and it is true. So we say we're going to reject the null and we figure out, hey, it was right. This happens a lot with medicines. You get some medicine and maybe it actually does cure what it's trying to cure, but we reject it. Because we say, I don't know, this, 2 or 3 of these people got really, really bad sick and the medicine didn't work on them, so maybe we should not try to use this medicine. And we reject it, and then maybe on down the road we find out that we could have been curing people for many, many years of whatever that disease is, because we rejected it. The type 2 error occurs if the null hypothesis is not rejected and you find out it's false. Same thing with the medicine. We say, oh yeah, this is a great medicine. And then it doesn't happen near as much as it used to, but back in the late 1800s, early 1900s, there used to be stuff like bloodletting and that stuff, and what they finally figure out, this isn't a good thing. Don't put leeches all over your body to suck out your blood. That's not going to cure you from stuff. It's probably just going to make you sick from something else. Seen something the other day on TV where they had it was from like 1910. It was some box they poured water into, and that water shot radon, or that box shot radon into the water to purify it, and then that way you could drink that purified water. Well, what do we know about radon now? Not good for you. So you were sticking that in there, and they're thinking, oh, now the water's purified because we're cleaning it out with this radiation, and probably several people died from radiation poisoning and they didn't even know it. So type 1 error occurs if you reject the null and it comes out to be true. Type 2, you fail to reject the null and it comes out to be false. Sometimes one of these is worse than the other, depending on the situation, right? If we fail to reject and the medicine, all of a sudden 5 years down the road we figure out the medicine causes leukemia or something, well, that's not good. And it could be on the other one too. USDA limits salmonella contamination for chicken is 20%. A meat inspector reports that the chicken produced by a company exceeds the USDA limit. You perform a hypothesis test to determine whether the meat inspector's claim is true. When will a type 1 error occur? When will a type 2 error occur? First thing we need to do. They're saying that, and this is a true statement here, this doesn't seem like a good thing, but you're allowed, as a chicken producer, you're allowed up to 20% of your chicken to have salmonella in it. Right? So that doesn't seem like a good thing because it's going to make you sick. So it's saying it's got a limit of 20%. That means our P, when we make our statement, has to be less than, let's see, limit for salmonella contamination is less than or equal to 0.20. That's their original statement. It's got to be less than that. A meat inspector reports that the chicken produced by the company exceeds this limit. So when we do this, we're going to do our HO. The company is saying that their chicken is, P is 20% or less. And our null hypothesis is going to be, and I might be telling you wrong because we might be going off of this meat inspector's claim here. The null hypothesis would be P is greater than 20%. Let's say we are going off the guys, and that means this is going to be the claim instead of the first one being the claim, because the meat inspector's making that claim right there. A type 1 error, if we go back for a second, a type 1 error occurs when the hypothesis is rejected, but it comes out to be true. A type 2, when we fail to reject it, and it comes out to be false. So if we look at this, we're making this null hypothesis, or we're looking at this null hypothesis here, and we're saying P is less than or equal to 20. Well, if we have a type 1 error, then we reject the null, and it ends up being true. So we say, okay, we don't believe that it's less than 20%. We reject that null, and then it ends up where it is less than 20. So what are we hurting there? If we say we reject the fact that it's less than 20%, are we hurting the people who are buying the chicken, or are we hurting the company that sells the chicken? If we're saying we don't believe that it's got less than 20% salmonella. Nobody sure. Hurting the company. We're going to make them throw away a bunch of chicken, and then we're going to find out, oh, the chicken was okay. So that's a type 1 error. We hurt the company if we do a type 1 error in this case. If we have a type 2 error, where we fail to reject the null, and then it comes out to be false. So we say, yeah, we believe the company. We're not going to reject their basis that it's 20% or less. We fail to reject that, and then it comes out that it was more. Who are we hurting now? The people who buy the chicken and get sick, right? Which one of those is worse then? Would it be better to make a type 1 error, or would it be better to make a type 2 error? Type 1 probably, right? Unless Nick owns the company that's selling the chicken, then he really doesn't care how many people get sick out here. He just wants to make the money and retire and get out, right? So a type 2 error here would cause people to get sick and maybe die. A type 1 error is just going to cause the company to have to throw away some of their chicken. So we did all that. P is less than or equal to 0.20. And again, I was wrong the first time because we were going off the meat inspector's claim. So here, we're here. This is the chicken's okay. Chicken's not okay. Type 1 error, we reject the null when it's true. So the actual portion of contaminated chicken is less than 0.2 or 20%. type 2 error, it's more than 20%, and we don't reject it. Again, on this one, we hurt the company. On this one, maybe people get sick. Type 2 error, you guys told me that. Type 2 error might cause people to get sick. Salmonella is not something that you want to mess with. Level of significance. This is important. Your maximum allowable probability for making a type 1 error. This is your level of significance. This is the symbol for level of significance is an alpha. Alpha. And it's that symbol right there. Looks like a fish. Looks like a peace symbol. Don't get it confused with sigma. Two different symbols. It's lowercase Greek letter alpha. By setting the level of significance at a small value, you're saying you want the probability of rejecting the null hypothesis to be small. Our level of significance, it's going to be like our levels last chapter where we had 90%, 95%, 99%, except this time it's going to be the other end. It's going to be like 5%, 1%, 10%. Level of significance. When we make it small, by setting the level of significance at a small value, you are saying that you want the probability of rejecting a true null hypothesis to be small. So we're saying this is what we're doing. Try to explain it this way.
Those are a chart for this one too.
Do what?
There's gonna be a chart for this one.
Yeah. At some point we'll use it. If our level of significance is 10%, then that means we're going to be way up here, and anything that falls in here, that's not good. That's the stuff that we want to get rid of. That's what we want to reject. If we use the level of significance at 1%, then instead of this line right here being way out here, that line might be way down here somewhere, and now we're only rejecting that. So that's what your level of significance is. How, if you make it real small, like 1%, 0.01, then we're not rejecting very much stuff. If we want to reject more stuff, because maybe like with the salmonella, people might get sick, so we don't want to get down anywhere close to where they're going to actually end up getting sick, we make the level of significance bigger. The ones that we use the most, 0.01, 1%, 0.05, and 10%, 0.10. Those are the ones that we use the most, just like the 99, 95, and 90 last chapter. Last chapter we also used 80 quite often, but we probably don't want to go out to 20% on our level of significance, because then we're letting in too much stuff that's false. Type 2 error is beta. This is a beta, it's a B with a little tail, extra tail on the end of it. So type 1 error, alpha, type 2 error, beta. Those are just the symbols that stand for them. After stating null and alternative hypothesis and specifying the level of significance, a random sample is taken from a population. Sample statistics are calculated. The statistics that is compared with the parameter in the null hypothesis is called the test statistic. Your test statistic is usually going to be mu, p. What's the other one that we use? Maybe sigma, standard deviation. Those are the ones that we use the most often. Oh, that was right there. I didn't realize it was on there. So your population parameter, mu p, and they use variance here instead. Mu p and variance. I think we use standard deviation more than we use variance. Test statistic would be x bar, p hat, and S squared. Just remember, these are the symbols for a population. These are the symbols for sample. We will still be using those charts from last chapter. You got your Z chart, you got your T chart, you got your chi chart. It's all stuff that we had last chapter. All right, on this assignment, page 367, 1 through 36, what I want to do is grab a book, open it up. We'll go through some of these together just to try to make sure that you understand some of it. I know Carson doesn't want me to do any of that for him. Yeah, it's not real hard. It's just confusing. Types of hypothesis. You did types of error. So number one is your null, HO. The other is HA. How are they related to each other? One word, starts with a C. Complements, good. Complements. The complements of each other. In other words, whatever's not in one is in the other. Somebody help me out, what's number two say?
Describe the two types of error, possible and hypothesis.
So now we got what? What's the first type? Type 1. What is type 1? Anybody remember?
We reject the null, but it's true.
Reject null, and it is true. So if we reject the null and it's true, we made a type 1 error. What's a type 2 error then? Fail to reject null and is false. Number 3, what are the two decisions that you can make from performing a hypothesis test? You can only do what? We just sort of stated up here. Okay, we can either reject null, or we can fail to reject null. Again, got to think about this stuff like a politician. Just because we reject the null, does that mean it's wrong? No. Just because we fail to reject it, does that mean it's right? No. That's why we're sort of acting like a politician, because we're saying, we're going to reject this. We're not saying whether it's wrong or right, we're just rejecting it. Trying to stay on the fence. Number 4, what's number 4 say?
Does failing to reject a null hypothesis mean that the null hypothesis is true? Explain.
And we just explained that, right? Just because we fail to reject it, does that mean it's true? No, it could still be false.
How do you explain it?
So it could still be false. Let's put no. Could be false. A lot of times what we'll say, if we fail to reject the null, could be that not enough, and the way we'll do it later on in the chapter, not enough info to accept null. Alright, so we're not actually rejecting it, we're just saying at this time we don't have enough information to say for sure that it's correct. Or to say that it's false if we fail to reject it, I guess is what they ask us. And we'll get into that more next time. number 5, I think number 5 is a true and false, isn't it?
Yeah.
I read it to me.
In the hypothesis test, you assume the alternative hypothesis is true.
Is that true or false? It's false. We assume what? Assume null is true. We always assume the null is true. Now, does the null have to be the original claim? No. So, but we're always going off of just the null. The alternative's just there to help us make sure we got everything. Number 6, what's it say?
A statistical hypothesis is a statement about a sample.
Is that true or false? It's not about the sample, it's about the what? Population. It's about the population. Now that one sort of confuses me because when it says a statistic actually deals with the sample, right? But we're making a statement from the sample about the population. So I'd never ever, that question, I don't like that question too much. But number 7, what's it say?
If you decide to reject the null hypothesis, you can support the alternative.
Is that true or false? If you reject the null, then what are you saying about the alternative? It's true, so that's a true statement. If you reject the null, then you're saying that the alternative must be true. Number 8, what's it say?
The level of significance is the maximum probability you allow for rejecting a null hypothesis when it's actually true.
So what they're saying there is, you know, we got, if we're on our normal curve here, we're saying how wide can we spread this? And our level of significance might be down here somewhere. So is that true or false? It's true, I think, isn't it? It's number 9 say. We'll talk more about level of significance as the chapter goes along. Don't worry too much about the alpha and the beta right now.
A large p-value in a test will favor rejection of the null hypothesis.
So in other words, the bigger our p-value, that's our level of significance, the bigger we make it, does that mean the more space we got over here where we're going to reject it? Yeah. Which one was that? Large p-value will favor rejection of the null hypothesis. Oh no, I'm sorry, that's wrong. I'm saying it wrong. Our p-value, not our alpha. Our p-value, if we have a large p-value, the p-value's this stuff in here. So a large p-value, is that going to favor rejecting the null? The wider we spread it, the more we're accepting it. So this is false. A large alpha value, should have read the question more carefully. Large alpha value would favor rejecting the null. What's 10 say?
If you want to support a claim, write it as a null hypothesis.
Is that true or false? If you want to support a claim, false.
Do it either way.
But we're always going to assume what? The null is true to start with, right? But that doesn't matter what we're trying to support. We're just assuming that for so we can do the problems. Number 11. Use a given statement to represent a claim, write its complement, state which is the null, which is the alternative. So on number 11, we're going to write the null. We're going to write the alternative. These are the ones you got to be able to do for this chapter. What's this original claim say on number 11?
Mu is less than or equal to 645.
Horrible writing. Can we put that in as our null or as our alternative?
Null.
Null. So we put that in here. And that's the claim, so we're gonna label it claim. That's the original claim. What's our alternative hypothesis gonna be then?
U is greater than 6.
I'm gonna let you do 12 through 16 yourself. Let's jump down. Let's do 17 through 20. Because they're just matching. Says match the alternative hypothesis with the graph, state the null, and sketch the graph. So we got an alternative hypothesis there. Mu is greater than 3. Which graph, A, B, or C? Shows us mu is greater than 3. See? Everybody agree with Sean on that one? Now they said also, write the null hypothesis, so HO, if mu is greater than or equal to 3, what's the null hypothesis gonna say? Mu is what? Mu is greater than 3, what's the null hypothesis gonna be? What do you do with the symbol? Flip it around, and we're also gonna put what on it? Equal to 3. Then we wanna graph that. How am I gonna graph that? What number has to be on the number line? 3. What kind of dot on 3? Is it a whole?
It's solid.
Solid? And which way do we wanna shade? So it should look something like that. Do what? No. You were right with C. Then they wanted us to do this to show the null hypothesis also. That's part of the problem. 18. Mu is less than 3. Mu is less than 3. Which graph shows us mu is less than 3? D. What's the null hypothesis going to be if that's our alternative hypothesis? Mu is what? If this is less than 3, then it's going to be greater than or equal to 3. Then we want to graph that new one. 3's got to be on our number line. What kind of dot on 3 this time? Solid again. And we shade where? Number 19, mu doesn't equal 3. Which graph on there shows mu not equal to 3? Just the 3 with the hole on it and everything else shaded, right? If mu doesn't equal 3, what's your null hypothesis going to be? Mu equals 3. What kind of graph's that going to look like? What number has to be on your graph? 3. What are you going to do with that? Just a dot on 3, right? That's it. You don't shade one way or the other. Mu is greater than 2. Well, there's only one choice left. I'm guessing that's probably it. Which one is it? A. What's our null hypothesis going to be this time? If mu is greater than 2, what's the less than or equal to 2? We go to shade, or we go to graph it. 2, what kind of dot on 2? It's less than or equal to? Solid, and which way do we shade? 21, it's probably the last one. It might be one of the word problems. 21, they tell us this, HO mu is less than or equal to 8.0. HA, what's HA gotta be then if HO is that? Do I even have to look back at the book to find it out? Mu has to be greater than 8.0, right? It's gotta be the complement of that. They want us to tell whether this is left-tailed, right-tailed, or two-tailed. So if we're looking at this, our mu, we look at this, mu, our null hypothesis, we're saying mu is less than or equal to 8. So 8's here somewhere on this graph. We'll say 8's about there. This is our mu's. These are all the mu's that we want because these are all the ones that are less than or equal to 8. Well, where's the mu's that we don't want? To the right. So what's that tell us? It's right-tailed. If you come up with a better way to explain that to everybody, let me know. Because that's drawing that little graph and saying, okay, all the mu's that we want are this way. The stuff that we don't want is on the right. That tells me it's right-tailed. So when the stuff you don't want, if you were to draw it, and the stuff that you want is over here, and the stuff you don't want is over here, then that's going to be what? Instead of right-tailed, it's going to be left-tailed. When we draw it, and it looks like this, and the stuff that we want is in here, this is the stuff that we're okay with, then that's going to be what? Two-tailed. Does that make sense? So we're looking at, this is what we're assuming to be true, right? We're assuming that the null hypothesis is true. So we're saying, let's make up a different one. Say our HO is mu is less than or equal to 5. And we're on our number line here. So we got 0 right there, 1, 2, 3, 4, 5, -1, -2, -3, -4, so on and so on, right? We want all the mu's that are less than or equal to 5. So we're here. All this stuff is the stuff we're okay with. All this stuff this way is the stuff that we're not okay with. That's the stuff where we don't want it to be there. We want it to be here because we're assuming that the null hypothesis is true. So if this is the stuff we don't want the right tail, and that's what that's called. So right tail. So this is right tailed. If the stuff that we didn't want was down here, then it'd be left tailed. Sometimes it'll be something like mu equals 12. Well, the stuff that we don't want is where mu's not 12. So we would have 12 here. That's the stuff right there on 12 that we want. All this stuff and all this stuff we don't want. So it'd be two-tailed. That's all the stuff that we want to get rid of or reject. Look at 21 real quick. Or not 21, 25. Just because I want to do one of these word problems, word problem first. A light bulb manufacturer claims that the mean life of a certain type of light bulb is more than 750 hours. So we want to write this. Their claim is mu is more than 750 hours. So how am I going to write that? Now, we wanna write the HO and we wanna write the HA for that. Well, this, right here, this original statement that we just translated into math, which one's it gonna be, the HO or the HA? HA. So mu is greater than 750. What's the, and we're gonna write claim out here with that. That's their claim. What's the HO gonna be then? That's our answer on it.